Okay. Hello everyone and welcome to today's session. I'm Michał Niciejewski. I'm a software engineer at CodiLime.
My name is Kułagowski. I work as a network architect at CodiLime.
And today we'll be talking about traffic offloading on GPUs, specifically about using GPUs for access control list processing. Let me first introduce the agenda. So first, we'll introduce the problem of packet processing in data centers. We'll talk about where the access control lists can be found in data centers and what are the issues and challenges in efficiently solving them. And next we'll be talking about our implementation of access control list processing on GPUs. We'll describe some GPU programming characteristics and our application design. Next, we'll compare our application to VPP, which implements highly optimized access control list processing module. And at the end, we'll summarize everything, and there will be a Q&A session. So if you have any question, feel free to ask. We'll take a look at the end, the chat, and answer all the questions.
Okay, let's start with the introduction. Let's talk about the data center architecture, devices in this place. So currently we have four major type of devices in the data center. We have switches, we have routers. Quite often they are the same as the switches, they share common hardware. And then we have firewalls as well.
And don't forget about bare metal servers, which don't count as network equipment, but actually can act as one.
So each device has a different role, has a different limitation, and has a different performance. Going from the bottom to top, switch is the fastest one. It's the simplest one. It works on the small number of fixed entries, of small number of MAC addresses, up to 8,000 entries. Each frame has a fixed size, a fixed entry, so processing such frame is pretty simple. So this leads to efficient hardware, leads to cheap hardware and very fast hardware. Then we have routers. Routers are still fast. They are slower than the switch, but still very, very fast. Why slower? They work on the bigger number of entries, up to millions of entries, but those entries are still very easy to optimize. We can use C3 algorithm to optimize such list of entries and search them way faster. And then we have firewalls. Firewalls are the most complicated. They deal with a different type of traffic, different type of the packet. Each packet is different. They are very complicated, and in result, they are slowest in the group. Why we cannot optimize firewalls the same way we are optimizing routers? Okay, let's talk in examples. So we have two examples.
Yeah, these examples aren't the real rule set examples. They are only to show some patterns that can appear in real rule sets.
So we have two examples. The first is the order. We have the first entry and the second entry. And if we change the order of those entries and the accept will go before the drop, the accept will shadow the drop entry. So this drop will never be hit. So we cannot change the order as we would like to, as we can do in routers on the switches. This is a pretty serious limitation. And the other example is we cannot aggregate entries into a smaller or wider ones. So here we have 3 entries ending with 0, 2, and 3. Since we are missing .1, we cannot aggregate them in the wider mask /30. Still, we have to deal with 3 entries instead of 1, which again is slower. So those two examples show us that not everything can be simplified, not everything can be easily accelerated in terms of firewalls. So we can deal with those issues in 2 ways. First one is stateful approach. So stateful approach works that each packet, the first packet of the flow, is affected by all the entries, is traversing all the rules. And then the result is placed in the flow table, and each following packet in the flow is not traversing via the all entries, but it's applied with the action that was applied to the first packet. So we are only searching the flow table, and then we are applying actions such as drop, nut, or something else. This approach is independent by the number of rules, but it's strongly affected by the number of flows. Since we are dealing with the larger flow table, we have to search the table, so it will take longer. So each packet will have to go through all the flow tables to find a match or not. And when dealing with the OVS, we can see that OVS will slow down significantly when dealing with the flows over 1000. And when we are dealing with the DDoS attack comes from multiple sources, are using multiple types of traffic, so they will create a huge number of flows, rendering such a stateful firewall useless, as the flow table will either overload or be very, very slow. On the other side of the equation, we have stateless approach. And stateless approach is, as said, stateless. Each packet is processed independently. There is no flow idea. So we are not affected by the number of flows, but we are strongly affected by the number of rules, since each packet has to travel via all rules in the ACL. As the ACL grows longer, the search times is longer and the firewalls slow down. So each side has advantages and disadvantages. Then we have to manage those ACL in some smart way. So we need to have a single point of view, single point of orchestration, some kind of console or user or automation system. And we also need to use some protocol that is already in the data center. We cannot develop a new protocol and expect all the vendors to implement it. And that protocol should be documented and should be open source, so everyone can use it. A BGP flow spec meets those requirements. So we've been using this in our R&D project. On the right side of this presentation slide, we have an example. We have a DDoS attack coming from the cloud on the right, and then we have orchestration. Orchestration sends an ACL update to the nearest router, and that router propagates those updates to all the routers along the way. The edge routers implement this firewall entry and stop the DDoS attack from reaching the web server. Here we are using BGP, open source, well known, well supported. It's a natural way to do such implementation. Then we have to locate that firewall somewhere, and we can locate that firewall close to the ISP. In such scenario, we'll be protecting north and south traffic. We'll have easy centralization because we'll have only few of them. It will be cheaper because, again, few strong boxes are cheaper than thousands or hundreds of thousands smaller ones. And the drawback is we'll have no protection from the inside traffic. If there will be internal DDoS from one virtual machine or one set of virtual machines or services to the others, such firewall location will not protect us. Then we can place the firewalls as close as to the bare metal server as possible. It will protect us also from the east-west traffic. It will be scattered across multiple points, but it will be expensive. If we'll be using dedicated device, then we will have to use as much devices as we have servers. So we are going into thousands and hundreds of thousands of devices, not cheap. Or we can place the firewall on the server itself, use a virtualized firewalls, but it will be cheaper, but it will consume CPU cores of the server. Those CPU cores could be used to customer service, could be used better, but they have to be used this way if we are integrating the firewall with the bare metal server. So when we are placing firewall or we are placing limitation of the traffic on the server, we can use few approaches. We can use advanced NIC, such as NVIDIA Mellanox ConnectX 5 or 6 series, and those series has some flow offload that can be dropping those float in the hardware, not affecting the CPU. We can of course use smart NICs such as NVIDIA Bluefield, Intel N3000. They are doing even a better job than the Mellanox, but they are pretty expensive and they are rare on the market. So sometimes you cannot order because the supply has dried out. Or, and this is what we'll be concentrating in the next part, we can use GPU. In this presentation, we'll be concentrating on the NVIDIA GPU, since it's the best documented GPU on the market, as we have found out. Okay, I'm passing my voice to Michał.
Okay, thank you. So now I'll be talking about implementation of our access control processing module on GPU. But first, a little bit about how we can program GPUs. So what are the differences between CPUs and GPUs? So CPUs consist of maybe few dozen high-performance cores. They are suitable for general and serial purpose tasks. So on the other hand, we have GPUs, which consist of thousands of cores, and they are weaker, but if we sum up the performance of these cores, we should still get much improvement compared to CPU. There's a downside though, because this GPU is not suitable for general tasks. They are suitable for parallel tasks and work in some specific computation model. But these restrictions allow for some hardware optimizations, which allow in turn for this better performance compared to the CPU. Okay, and how does this operating model look like? So I will describe it with the example of pixel shader. So here we have an array of pixels, and we want to execute some code on every pixel in this array. In general, we can have millions of pixels, and we maybe want to execute this operation a few times per second. So we need a tremendous amount of computational power to do it. And GPUs are optimized for this case. We can have they operate in what's called SIMD model, which is single instruction, multiple threads. And this means that a single instruction is executed by multiple threads, in this case executing this common shell code on multiple pixels at once in parallel. If we wanted to execute different code on each of these pixels, this would work much slower. So it's important that this code is common. What's interesting is that we don't need to restrict ourselves to image processing, as long as our algorithm can be expressed in this SIMD model. We can probably use GPUs for executing it. And in our case, it's important that usually traffic filtering and general traffic processing code can be expressed in this model. We have an array of in this case, packets, and we want to execute some common code on every packet of this in this array. So again, we can take every GPU core can execute some common filtering, in this case code, on every packet in this array. Okay, so now we should have some intuition that GPUs can be used for traffic processing, but there are still some technical problems that we need to address first, and I will focus on one of them, specifically how GPUs can access packet data. And here's a reminder how a typical CPU application, network CPU application work. So let's say a packet arrives to the NIC, and NIC writes this packet to CPU RAM. Then CPU application, network application, reads this packet and processes it. And yeah, you can see that it's quite straightforward and nothing complicated here. And let's say we want to move this packet processing to GPU, and we can choose one of several ways how to do it. And here I describe this one where we copy the packet from CPU RAM to GPU RAM. So here packet arrives, it is written to CPU RAM, and then some CPU application runs and schedules a copy of this packet to GPU RAM, where it can be processed by GPU. So it actually starts looking a little bit complicated, and we have also, because of this copy, the latency of the operation increases. So it's not that good anymore. And we can actually do it a little bit simpler. And there is a technology called NVIDIA GPU Direct RDMA, which allows for allows NIC to directly write packet data to GPU memory, where it can be processed by network application. And this allows to reduce this latency.
And more importantly, this approach saves the CPU core. It goes directly bypassing RAM and CPU at all.
Yes, exactly. Okay, so now we can move on to the application design. So let's say a packet or a batch of packets arrives to the NIC. Then they are written to GPU RAM via this technology, NVIDIA GPU Direct RDMA. Next, some CPU application, in our case it was DBDK application, notices that packets arrived and tells GPU to start executing this access control release processing algorithm on GPU. The algorithm reads this code reads the packets and processes them and writes outcome to some common memory. In our case, it was just CPU RAM. Next, the DBDK application reads the outcome that was written previously by GPU and decides what to do with the packets. The packets are either dropped or forwarded to the network. In this latter case, NIC reads the packets from GPU RAM and sends them to the network.
Yes, in this case, we are using CPUs, but only for the packet management. So all the ACL processing is still happening in the GPU, but we are using just a few cores, way less core that we'll be using for the ACL, just to manage the outcome of the ACL processing.
Okay. And the last thing I want to mention in this implementation part of presentation is our access control release processing algorithms. We actually implemented something more sophisticated than just a naive algorithm which iterates over the rule sets and finds the first rule. We've implemented the tuple space search algorithm, which is also used in Open vSwitch, and compared it to tuple merge, which is implemented in vector packet processing. And this tuple merge algorithm is actually an improvement of tuple space search. We won't talk about details of this algorithm, but if you are interested, I recommend checking our blog about these algorithms.
Now let's talk about the results that we achieved with our approach. Before we go into that, let's describe the environment that we've been using to test and check the ICL processing. We've been using a common server manufacturer, Supermicro. It's available worldwide, so everyone can buy it. We've been using a CPU that is equipped with 16 cores. 4 cores were used for the GPU. Most of the remaining cores were used for the traffic generator and traffic accounting. The memory amount was 128 gigabytes, and we've been using 2 network cards for traffic sending and returning, as seen on the picture on the right. So we've been 3x traffic generator based, fueled by DPDK. The traffic has sent the packets were arrived on the GPU was doing all the filtering and sending back the results to the traffic generator for the accounting. And as for the GPU, we've been using NVIDIA Quadro RTX 4000.
Yes, and this GPU card is actually not the newest one. It was released about 4 years ago, so but we still got some quite good results, which we'll show you in a second.
So first result is the throughput, how fast we can go, how many packets per second we can achieve. We've tested multiple rules scenario from 100 to 10,000 flows. The matching entry was always the last one. So in the naive world, the packet would travel by all entries in the ACL to be matched by the last one. And we can see on the graph presented on the right that with the blue line, this is our result with the GPU. We achieved 25 megapackets per second, which is, I would believe, pretty good. In comparison, we are showing the results of the VPP. VPP is data plane maintained, developed by Cisco and open source community. And we checked with different core assignment for the ACL processing from 1 to 5. Still, they were way lower than our results. We estimated that we would need 30 cores to match our GPU performance, what is more important is we have steady line even when the ACLs grows longer. However, with the CPU software processing, the performance is dropping as the ACL grows longer. So we are independent from the ACL size. We are still having same amount of packets per second. On the other hand, we have latency results, and latency is again compared to the software solution as mentioned VPP, and we have found us in the lower parts of the VPP. So on the right we have diagram, and the blue on the green field is the latency created by the software processing packets by the VPP between 1 and 5 core assigned, and the blue line is our result. As you can see, we are in the lower parts, so we are pretty good. There is a slight growth, but not that significant. We're around 50-60 microseconds per packet, and the number of the rules are placed on the x-axis on the graph.
Okay, and if you are interested in detailed comparison and more graphs, and you can check our blog. Yes.
Now let's talk about the alternative use cases, and let's do a summary of this presentation. On the slides previously, we've been using GPU as a typical inline firewall, but this is not the only case we can use it. We can use the GPU as a firewall between software switch, such as OVS, and the virtual machine. It can be used as a plugin for the VPP. The VPP supports multiple plugins. And here on the left, we have a typical deployment scenario. We have a VPP or OVS working as a virtual switch and with the firewall function. And packets arise on the physical interface. They are being processed by the virtual switch. And after ACL, they are hitting or not a virtual machine and the container. As you can see, we have to assign plenty of CPU cores and a few cores for the virtual machine. If we'll be using GPU here, we will have to assign, of course, few cores, 2 or 4 for the GPU, but we would have to assign way less cores for the VPP. So at the end, we would save 5 cores that can be used for the virtual machine and the container. Of course, with the bigger amount of traffic, the gain will be more significant. This is just an example showing us that we can save cores and plenty of them.
Okay, so are the GPUs suitable for networking? We have several advantages. First, we can free some CPU cores from traffic processing and use these cores for other purposes, for example, assigning them to virtual machines. And next, we can get a huge performance boost at much lower cost compared to the CPU setup. Also, thanks to this direct NIC to GPU communication, we can get quite good latency. If you want to compare GPUs to other hardware solutions like SmartNICs, then GPUs are much more popular. They are widely used for general purpose programming, so they should have less problems. Also, if we write a code for one GPU, it should work for many other GPUs without changes. We are actually using NVIDIA GPUs, so our code would work only on NVIDIA GPUs, but still there are many NVIDIA GPUs. And also there are some disadvantages. For example, we need a server that is capable of hosting a modern GPU. In our case, we needed some additional power source for the GPU. And also, using GPUs in networking is quite a novel approach, so there still are many problems that are not well documented yet.
But we are finding more and more projects using GPU as an accelerator to some work. And even recently, NVIDIA has released a patches or support in the DPDK. So this is making approach to use NVIDIA in network work way easier. Okay, this sums up our presentation. Now let's go to the QA question. There is already a question at the chat.
Okay, so have you found any bottlenecks during testing, for example, reaching max speed of PCI Express, SmartNIC, or network traffic? Yes, actually, we've reached some bottlenecks. Some of them were solved, but I can talk about one which we haven't solved yet. And if we go back to the results, okay, so here you can see that we have 25 mega packets per second, and it is constant. And we actually could reach much better performance here, but we think that there was some problem with this NVIDIA GPU Direct RDMA technology that we couldn't solve. We think that it was related to PCI topology, but as I said, we haven't investigated it enough. And we actually have an additional slide where have a theoretical performance that can be reached with this GPU. And here we eliminated this copy from NIC to GPU and just place the packets directly on GPU and process them without any copies from NIC or something like that. And we could reach much better performance, even in some cases up to 2 times better performance.
The second question about the GPU power consumption, do we have any figures? Well, it's a little bit related to the first one. We have found out that the NVIDIA scales quite aggressively to limit power usage. Unfortunately, when to save power usage, it also brings the CPU clock way down. So at the end, suddenly, in the middle of packet processing, the performance was dropping rapidly. So we have to force NVIDIA to work at the highest clock speed to have the constant performance results. So yes, the power consumption would be higher, but not that higher depending on the GPU we would use. There are GPUs that do not require external power supplies. They will give us lower performance, and there are GPUs that consume plenty of power, but they will give us the best performance boost.
Can the XXV V710 do direct DMA to the Quadro GPU? Also, have you tried? Okay, so the first question, yes, we've done exactly that, and actually there is restrictions on GPUs for this direct DMA usage, because we had to use Quadro card and not GeForce ones, because GeForce doesn't support this NVIDIA GPU direct DMA technology. So it's more problem with there are more problems with GPU cards than NICs in this case. And have you tried direct DMA on the Radeon Pro? No, we haven't tried it. By the way, this direct DMA, we also have a slide for it. It's something similar to GPU direct DMA, but for AMD's cards. And but yeah, we haven't tested it. Okay, and the second one, is it possible to initiate a transfer from the GPU towards the NIC without any CPU DBTK involvement? I think it would be possible, but it would require a lot of additional implementation, because we would need to port most of the DBTK to GPU. So it could, for example, access appropriate registers of the card. We would just need to implement the driver for this NIC. So I think it would be possible, but would require a lot of work.
And it could be not worth the cost, since we are only using 1 or 2 CPUs, even with that amount of packet processing, and it's easier and well supported and imposes minimal patches to the current workload.
Okay, how does host-bound traffic handled?
That depends on the scenario. We've been testing traffic where all the traffic is flowing through the GPU, so there was no inbound traffic. It was just an inline firewall, just processing traffic along with the ACL or not. To support inbound traffic, you would have to change the architecture and implement our solution as a plugin for the VPP. And in such scenario, it would be really possible, because the packet will be passed back to the graph of VPP, and the VPP would do the rest. So that would be a better approach to also support the host-bound traffic.
Okay. Have you tried the DBTK GPU dev library for this application? No, we haven't used it, because we started this project before it appeared. We started it about 1.5 year ago. So, but yeah, we are aware that it exists, but we already had much code that we didn't want to port to the library. But yes, we appreciate that it's present. Okay, are there certain primitives not available on GPUs because GPU cores are meant for matrix math? I imagine GPU cores do not have all the capabilities of CPU cores. Okay, so in our case, we didn't have many problems with GPUs. Of course, they are optimized more for this matrix math, but in our case, it worked fine. We used CUDA programming language to write all of our GPU code, and it allows for I don't know. It looks like everything what was needed for our project was available. But yes, of course, there would be some limitations and something would work slower because it's on GPU, not on CPU. Okay. Is there an upper limit on capacity? What is that? How does it affect performance?
By capacity, there is number of rules.
Okay. So we haven't tested this because we've tested 10K rules because we think that it's actually pretty much the most rules that would appear. But I think no, that there is not such a limit. We think that if we added more rules, then we could easily it would work fine. And
of course, at some point we'll run out of memory, but
yes,
let's be honest, newest GPU has plenty of memory, so there's plenty place to use it.
Mm-hmm.
Okay, new customer grade Radeon cards allow direct connect to the GPU. Will you test it to make it more cost effective? No, at the moment. Okay, bad answer. At the moment of writing, the moment of this work, we've been using only NVIDIA, as only NVIDIA was available easily. Please in mind that most of the work was done in the COVID era when the availability of network cards was very, very limited, as most of us you recall. But the new Radeon cards, that sounds pretty promising, and we will consider it. We will just need to check it if they are available in our area.
Okay, so is there any other question?
I think we ran to the end of it. Okay, let's give us a minute or two for more questions. There will be a survey at the end of after the presentation, after the webinar will end. It will be sent half an hour after. Please fill it so we will know better what part was most interesting, where did we did wrong or where did we good, and this will allow us to make next presentation way better than this one was. Okay, thank you for joining our presentation. Thank you for listening.
Yeah, exactly. Thank you and for participating.
And see you on the next webinar.
See you.
Thanks. See you.